All right. Right now we have Recitation 4 and Problem 1, and we are given an idle gas, and it's contained in a vertical piston assembly by a frictional piston. The mass of the piston is 40 kilograms, and the area is 0.02 meters squared, and then the mass of the gas is 2.5 grams, and initially occupied in a 5 liters, that's the volume, and a hot plate slowly transfers eventually into the gas. So this is Q in. Okay? Via heat transfer, increasing the absolute temperature by 30%. So T1 times 1.3 equals to T2. And if the atmosphere exerts pressure of 100 kPa, so this is P atmosphere, on the top of the piston, determine the change in specific internal energy of units in kilojoules per kilogram. Okay, so we know it's an ideal gas, so we know that PV equals to MRT is applied, and we know that the mass of the piston, so MP equals to 40 kilograms, the mass of the gas is 2.5 grams, and that would be just 2.5 times 10 to the negative 3 kilograms, and we know that the volume is 5 liters, and that is just 5 times 10 to the negative 3 meters cubed. Okay, and hot plate solution and Q out is 2 kilojoules. Q in, not Q out. Q in is 2 kilojoules, and the heat transfer, and then T1 times 1.3 equals to T2, or 1.3 T1. Okay, and we want to find the atmosphere. So let's start with our schematic, because that's always required for the 7-step process. And so here's our piston, and here's our system boundary. And we know that there is Q in. And since the volume is changing, we know that there's boundary work. But where does it point exactly? We don't know yet. Okay? So what we want to do is from the free, now we do a free body diagram from the piston. So from here, we have both the pressure of the atmosphere, P atmosphere, times area, and then we have the weight of the piston, and then we have the pressure inside times the area. Okay, and all of this are the forces in Y. So we can say P times 0.2, because that's the area as well. Yeah. So area is 0.02 meters squared. So we can just plug everything in. So P would just equal to P atmosphere times area plus mg over the area. That would just be, so 100 times 10 to the third times 0.02 plus 40 times 9.81 over 0.02. So we get 100, and that would just all equal to 119,620, and that is in pascals, and you just convert them by 119.62 kPa. Okay, that is your pressure, the internal pressure, and we know that both of the other, we can assume that they're constants, both the atmospheric pressure and the weight. So P1 would equal to P2. And now from the ideal gas law, we know that PV equals to MRT. Okay, and we can just, we know that pressure is constant. Okay, and then we know that the mass is constant because it's closed. It's a closed system, and then R is constant because we're just using air, or it's R is always constant. So we can just move all of these to one side and move around. So we just moved the volume here and move MR over here. So since these are constants, we can just say that T1 over V1 equals to T2 over V2. And we know T2 is 1.3 T1. So V2 is just 1.3 V1. Because we increased T by 1.3, we have to increase V by 1.3. So since we know now that our volume is increasing, okay, not by, we don't know the amount, but we know it's increasing. And when volume is increasing, we know that V2 minus V1, that's going to be a positive number. So our boundary work would be PdV, or V2 minus V1, because the pressure is constant. It would be a positive value. So it would be work out. So from that, we go back into our schematic and add our boundary work. Okay? Or we could just say work out instead of boundary work, but you know, it's the same. Um, Now that we know everything, we can calculate our boundary work by just figuring out from the ideal gas law, we can figure out our volume. Or no, we don't need to figure. We're given V1. So we're given V1, uh, which is this. So 5 times 1.3 is 6.5. So V2, so V2 would equal to 6.5 times 10 to the negative 3, and V1 is 5 times 10. And the difference from that for this would be 1.5 times 10 to the negative 3 times 119.62. So, and it'll be 1.17943 kilojoules. And from the energy balance equation, you know, U plus delta KE plus PE plus delta PE equals to in plus work in minus work out plus E mass in minus E mass out. So we cancel these out because it's closed. We cancel these because it's stationary. And we know there's no Q out, and we know our work is work out, not work in. Okay. So we can, we want to change, yeah. So we know Q in is 2 kilojoules. So 2 minus our value that we found, 0.17943. That would be 1.8206. And this is delta capital U, and this is in kilojoules. And then we just divide by mass, equals to delta specific, which is just divided by 2.5 times 10 to the negative 3, because it's the air, and we'd get 728.23 kilojoules per kilogram. That is your answer for question 1. So for question 2, we're given a rigid sealed metal tank with an interior volume of 0.8. So this is V. And because it's rigid, it's equal in volume. So V1 equals to V2 as a saturated vapor. So we look at the tables and we have it at 100, and the tank is then placed in a room of 40 and left until it reached equilibrium. So T2 is 40. And with the surrounding, draw the schematic and identify the system under something. So since it's rigid, or there's no change in volume, there's no boundary work, and there's no work stated of how much, if there's like work in or going in or out. And we know that the temperature is decreasing, so there is Q out and not Q in. So when we draw our schematic, here's our box, and here is our system boundary. It's only inside, and we only have Q out. Okay. Uh, so now for the TV and PV diagrams, we know that the volumes are the same. The specific volumes are all the same because it's a closed system and mass is not changing. So, and we know we start at a saturated vapor, so we start at this line and we just go down because the temperature is decreasing, and we draw our isobars because isobars start from the bottom. We just draw this first. So this is P1, P2, state 1, state 2, and it goes down. Okay, and for the other part, because we know from this that P1 and P2, P2 is lower than P1, so we can just do the same for this. If this is on the vapor, it goes down, and then our isotherms and isotherms go down. So let me just do this. State 1, state 2, T1, T2, and then we just like label this like this is V1, V2, and then this is V1, V2. Okay. And then determine the heat transfer in kilojoules during the equilibrium process. Okay. So from the property tables, we know it's a saturated vapor, and we start at 100. So this is saturated vapor. These are our volumes, specific volumes, and these are specific internal energies. And we do the same for 40 because we're going down and we know we're going into the saturated mixer, so we don't need to look at the superheated or the compressed liquid tables. So, and we know it's a vapor, so we know that this is our specific volume and this is our specific internal. So let me just write that down, 2.56 and 1.672. So our U1 is 2506 and V1 is 1.672. This is in kilojoules per kilogram, and this is in meters cubed per kilogram. Okay, and we know that it's a rigid tank, so we know this is also equal to V2. And because we know this is V2, we can find the quality V2 minus V of F over V of FG, or we can just say Vg minus V of F. Okay, and from that we have 1.672 minus whatever these values are. So 8, and that would be 1. And our quality would be 0.0856. Okay, and from the quality we can find U2, and that would be x times U of fg plus U of f, and that those values are over here. So 2261.9 times this plus 1.67.53, and that would be 0.056 times 2261.9 plus 167.53, and that would equal to 361.21. And from that we could find our change in internal energy. So U2 minus U1 would equal to, so it's 2506 minus 361.21. That would be 2144.79 kilojoules per kilogram. And we want to find the capital U, change in capital U, and we would just multiply it by the mass, which we could find from the internal, because it says in kilojoules, yeah. So we can just find the mass by doing capital over V little, and that would be 0.8 divided by 1.672, so it's 0.8 over 1.672, that would be 0.478, and then we'd multiply that, so delta U times mass, so it's this times that, and it would be 1026.21. And now from the energy balance, we know it's stationary, so there's no kinetic, and we have internal, there's no kinetic, no potential for stationary. There's only Q out, and then we don't have any boundary work or any work because it's rigid, and we don't have any mass flow in or mass flow out because it's a closed system. So Q so this would also be 1, 2, negative. This should be a negative value. This should be negative, and this also should be negative. So Q, so this is just going to be like negative 1026.21. So Q out equals to 1026.21 kilojoules. And that is your final answer.